Okay, I've got 2 minutes past, and I think the login list is pretty much converged. So why don't we get started for the day? We've got a little bit in the way of logistics to discuss. I can't believe that this is the last week of new material for quantum mechanics. So today we will discuss the variational principle, and on Wednesday we will discuss quantization of the electromagnetic field and photons, woohoo, which is a nice bridge topic between fixed number of particles, quantum mechanics, and quantum field theory, which I will be teaching next year and hope to see many of you in. So the logistics that we need to discuss are the take-home midterm. I posted that on Friday very, very late at night once I finished verifying that it worked as intended. I'll run through that in a minute. That is due in 2 weeks, so not this Friday, but next Friday. So you've got time to work through that. That is comparable in length to what the first midterm was that you guys had an hour and a half-ish to do. This, you can take your time and solve it at home. So we'll go through this and what's on it. Correlated with this is the homework cutoff. The homework cutoff is this Friday for back homeworks. So I will accept everything up through this Friday with no late penalties. But as of midnight on Friday/Saturday, then I have to cut it off, and you haven't submitted it, then you get a 0 for it. But you're still welcome to submit corrections to the homework, including corrections to a 0 anytime through the very last day of the semester, as long as you're willing to take your chances on whether or not I have time to grade it. So you will still have a chance to submit corrections. At the moment, these are the numbers. I have 10 submissions for number 6, which is almost everybody, and I've got 6 apiece for homeworks number 7 and 8. So I think people are converging. Hopefully, you guys will get there in the next few days. Feel free to come ask me questions. Drop me a message anytime. I will try and answer any questions to help you get through this between now and then. I think that's everything as far as the agenda. Any logistical issues that we need to discuss aside from this before I flash what's on the midterm and walk you through it? Question?
Are you going, for example, to drop the lowest homework grade, or you don't plan to do this?
I had not planned on that, but I'm open to the discussion. Why don't we see what things look like next week when we're going through the sample exam? Especially homework 4 in particular. That was the one that most people struggled with. That was a ridiculous amount of algebra. It was very hard to give partial credit on something where if you made a mistake on page 1 and then went off the rails, it was very hard to...
It's not physics in it.
There's physics in it, but it's very discretized. It's very quantized in terms of how people did. So I'm amenable to the idea. I hadn't thought through the implications of it. So maybe let's discuss it some. Maybe Canvas would be a good place to have another discussion board. Does that answer your question for now? We can continue discussing that in the next week or so. Other logistical concerns.
Any chance we can net a point by doing the course evaluation?
Oh, course evaluations. Yes, thank you. Yes, please do the course evaluations. That's a fair suggestion. Maybe I can bribe people to complete the course evaluations. Course eval. I will consider a nominal bribe to encourage people to do that. Okay, any other logistical issues that we should chat about before I walk you through what's on the take-home midterm? Okay, let me jump on and share screen for a second then. So here's Canvas. Let me switch over to student view so you see what I see, or I see what you see. Okay, so here's the stuff for today. Let me open that in a separate tab because, boy, do we have some stuff to talk about. Past assignments, upcoming assignment, midterm number 2. So this one is worth 50 points, the same as the previous one. The format is the same as before. So for this one, there are 6 conceptual questions. That is 2 each for the 3 topics that we discussed, which is time-dependent perturbation theory, atoms in external fields, and scattering theory. So you've got 2 questions very similar to the conceptual questions that have been on the homework. Given a hydrogen atom initially in the n=3 state and a pulse of this particular form, then tell me what levels can be occupied as t goes to infinity. Very similar to what you guys did on the homework. A similar exercise about fast and slow perturbations. So if you start off with the wave function of tritium, which is hydrogen but heavy, it has a proton and 2 extra neutrons that doesn't do anything else to the potential. So it starts off in this particular state, but then suddenly it undergoes beta decay. And one of those neutrons turns into a proton. So the Z of the atom changes. Now this is no longer an eigenstate of the new Hamiltonian that has a different Z value. And so this is an exercise in time scales and time-dependent perturbation theory. So if the time it takes for the beta decay to occur is 3 times 10 to the minus 19 seconds, then what will the wave function of the electron be after this is complete? So this is a sudden versus adiabatic kind of discussion. To answer this, you need to figure out what are the time scales associated with the atomic transitions and compare this time scale to them. This looks like a really small number, but there are other really small numbers in the atomic time scale. So you've got to compare them to each other. Next 2 questions on atoms and external fields. Again, very similar to what we had before. Here you have a Hamiltonian of a particular form, x times z. I asked you to deduce the selection rules. Very similar to the quadrupole tensor exercise on homework 7. I give you, for your reference, in Appendix A, the various vector and quadrupole spherical tensor decomposition. So these are exactly the combinations that carry L equals 1, M equals plus 1, 0, minus 1, and L equals 2, M equals plus 2, plus 1, 0, minus 1, minus 2 units of angular momentum. So you will use that knowledge of angular momentum to determine the selection rules associated with the operator GXZ. Similarly, here I give you a particle which is in the ground state of the three-dimensional harmonic oscillator, and I ask you how it will depend on the electric field linearly or quadratically under the Stark effect, the leading order. Okay, so that was the 2 questions for atoms and external fields. The 2 questions for scattering theory. Again, similar to the conceptual questions on the homework. One of them related to the meaning of a cross-section. Here, this is about how much beam time will it take. The term in the field is instantaneous luminosity. So if the instantaneous luminosity, which is another way of saying the beam current is given by this, the object has a cross-section of this, how much time will it take to produce one of them? This is an actual question that you need to know when you are designing a particle accelerator if you want to discover a specific particle. And lastly, relating to scattering theory, if you have protons with a specific kinetic energy and you're interacting with the potential of a given depth and a given range, which approximation is the one you're going to want to use? We talked about both Born approximation and perturbation theory, and we talked about the partial wave expansion. These are both good descriptions, but in different energy regimes. So I'm asking you to look at which energy regime is the one that you want to use in this case. Okay, so those are mostly, order of magnitude estimates, comparing length scales of things. 3 points each for the conceptual questions for a total of 18 points. The balance of 32 points goes into the calculation. So this was a more calculation-heavy exercise. Again, similar to the exercises you had in the homework. Given a one-dimensional harmonic oscillator and a perturbation of this type, calculate the transition probability. You may or may not want to take advantage of contour integration on this, the same way that you did on the homework. Again, for problem 8, you have a particle in a one-dimensional harmonic oscillator starting off in the n equals 1 state, and then you're supposed to calculate the transition rate to first order in perturbation theory. That should be ringing bells in your head about Fermi's golden rule. Again, elementary applications of the core things that we derived associated with time-dependent perturbation theory. For problem 9, this is a calculation of the Stark shift. Particle is in a harmonic oscillator state. It's actually a combination of the 2 eigenstates. So in any one of these states, the expectation value would be 0 at first order, but in this particular superposition, it doesn't have to be. So calculate the first order Stark shift. This is a pretty straightforward exercise. For problem 10, this is again a very straightforward exercise. I'm saying, imagine a spin 3/2 particle with L equals 1 and G factor 2. Calculate the Zeeman shift to first order. So tell me how many distinct levels there are and what their energies are under the Zeeman effect. Pretty elementary stuff. And then the last 2 are 2 problems on scattering theory. Calculate the cross-section and calculate the S-wave phase shift. The cross-section for a given potential, the potential I gave you is the delta shell potential. So something which is just a delta function for a given radius in 3 dimensions. This is about the simplest potential that I can toss your way. And then for problem 12 with the phase shifts, this becomes quite messy. I'm not asking you to solve for it. I'm just asking you to derive the equation that determines the phase shift. You do not have to solve this. You don't have to do anything else with it, but derive this particular expression for the phase shift. If this looks familiar, it is. The problem we solved in class that was based on the comprehensive exam was the delta barrier potential, where you had 0 and positive V naught, and the energy was less than V naught, so you've got some decaying exponentials inside. In this one, it's the delta well, so you have a negative V naught, and you don't get hyperbolic stuff, you get regular trade. But other than that, this problem is very, very similar to the one that we discussed at the end of class on scattering. And then the appendix, as I mentioned, is just the table of spherical tensors. Any questions or concerns on the exam? As I mentioned, you have 2 weeks to do it. It is due next Friday. And then as of this Friday night at midnight, you will have the homework solutions as well to guide you through this. Any questions or concerns on this or any other course logistics? Okay, if not, then let's dive into one of the last topics for the semester. I really didn't want to spend a lot of time going through the variational principle because I think we're going to derive the entire physics content of it in the first 10 minutes. And everything else is just going to be a laborious exercise in algebra. You will do a lot of calculation for not a lot of physics insight. It tends to work, but you don't necessarily learn a whole lot out of it. If you note online the length of the notes for today, there is no way on earth we're going to be able to get through all 16 pages of this. My hope is that we will get through about the first 7 or 8 where we derive the main physics ideas and a few simple examples. But I wanted to work through the example from the 2017 comprehensive exam. And when I sat down and started working on that yesterday, that turned out to be much longer and much more involved than I anticipated, and that made me extremely angry. We'll talk about that in a little bit. I think that was an incredibly unfair question to put on the comprehensive exam for you guys. And for that reason, I wanted to ensure that you had all 8 pages of the solution to that handy for your own reference. Okay, variational principle, what is it? There's only one physics concept which enters into the variational principle, and that is, by definition, ground state is the minimum energy. The ground state energy E naught is the minimum energy of any eigenstate. So if you have a Hamiltonian H and I call its eigenstates n and eigenvalues En, then let me call n equals 0 the ground state. Then the definition of what I mean by the ground state is that the energy of the ground state is less than or equal to all Ens, no matter what they are. This is a trivial tautology. Ground state means the minimum energy. The implication of this, however, is that because the eigenstates are a complete basis, this is also the minimum energy you can ever get for any wave function. And that is the basis of the variational principle. So since the eigenstates are a complete basis, this remains true for any wave function, not just an eigenstate. Any wave function in the Hilbert space. So if I calculate the expectation value, the average energy in any particular state psi, then I can insert a complete set of states corresponding to the eigenstates. So I can write sum over I and sum over j going from 0 to infinity. And then I have psi I Hamiltonian j psi. I've just inserted a complete set of eigenstates. Since, by definition, these are eigenstates of the Hamiltonian, this matrix element of the Hamiltonian is simple and diagonal. This is delta ij E sub j. And then I use the delta ij to collapse the sum. So this is sum I equals 0 to infinity. Let me say j, since I decided to call this one j. E sub j psi j psi. All I've done is insert a complete basis, and now all I'm going to do is use this definition. Whatever energies I have here, they must be at least as big as the ground state energy. So it trivially follows that the expectation value of the Hamiltonian, which is the average energy associated with this wave function, is less than or equal to sum I equals 0 to infinity E0 sine I psi. I think I switched from J to I, sorry about that. All I've done is I've said for all E sub j is greater than or equal to E0. I think I wrote my equality backwards. That's important. And I think I screwed that up on my notes as well. Yeah, so the left-hand side is the sum, and these energies are always greater than or equal to E0. After I've replaced this, this is just a constant. And so I pull it out, and then I can remove the complete set of states again. So for I psi, this is just 1. E0, and then I get the overlap of psi with itself. If psi is a properly normalized state, then this thing is equal to 1. But often, when we use the variational principle, we won't bother correctly normalizing. Equals 1 if properly normalized. And this gives me the result that I wanted. The ground state energy is less than or equal to the expectation value of the Hamiltonian divided by the normalization of the wave function. And this is true for any psi in the Hilbert space. All right, the physics of the variational principle, that's it. Everything else from here on out is math. One thing that's appealing is that this translates the exercise of finding the ground state energy into a minimization problem, similar to the exercise of constructing the action and the classical solution of classical mechanics as a minimization problem of the action. So this reduces to a minimization problem. One thing that you can do is if you express this in a position basis, then I can write this as an integral over wave functions. So one can write the ground state energy is equal to the minimum of this expression, integral over all space, complex conjugate wave function, Hamiltonian operator, wave function, divided by normalization. And this is a minimization exercise over all wave functions. Psi of R. This is the expression in 3 dimensions. It's trivial to see how it simplifies if you're doing it in 1 dimension instead. So what this means is that for any particular function that I pick, I can evaluate these integrals and I'll get a number. What I want to do is I want to minimize for any choice of that infinitely complicated function. Any function you can imagine that could live in your Hilbert space. You need to find the minimum of that ratio for that function. So one way that we can express this is to define this object in brackets here as the energy functional. This is the energy or the average energy associated with the choice of a particular function. So let me write E bracket psi of R, defined to be that integral. Integral d3r, psi star Hamiltonian psi over integral d3r psi squared. So this object is a functional. So this means that the effective energy or the average energy that you get depends on the function, but it depends on it in a non-local way. This is different from saying I have some function f of x, where you plug in a number for x, you get an answer. Here, this depends on the behavior of the function everywhere over all space. So if you take a function which looks like, I don't know, a Gaussian, and you change it just a little bit at one point, changing the wave function anywhere will change the value of this integral. So this is a more complicated dependence than just f of x. This is a dependence on the entire functional form of the wave function. This is not so alien to us. We already encountered a functional last semester, specifically the action. So cross-reference the action in classical mechanics. The action S is a functional of the trajectory Q of t. The action was defined as integral dt Lagrangian of Q of t, Q dot of t, and maybe even time explicit. So in the same way, the action is an integral that depends on the specific functional form of the trajectory that we picked. So we have some experience in minimizing a function. What we found from this is that when we minimized the action, what we got were the Euler-Lagrange equations. Which determine the classical solution in terms of the Lagrangian itself. If we really wanted to, we could apply that same technology here and find the critical points as a function of the arbitrary wave function psi. But there's no point in even trying, because if I do that, I'm just going to get back the Schrodinger equation, which I don't know how to solve. Otherwise, I wouldn't be doing the variational principle in the first place. So even if we could try to minimize this functional dependence exactly, it would just spit back the Schrodinger equation. So we don't want to do that. Instead, we want to approximately minimize this thing over some limited space of functions. So instead, minimize psi, or minimize the functional E of psi over a limited space of functions. Limited or truncated set of functions. There are a couple of different ways to do this or think about it. One which I think is appealing is to say, well, I can't minimize it, or I don't want to try to minimize it over all possible functions, so let me pick a basis. And I'll pick a basis for a limited subspace, and I'll minimize it within that basis. Pick a truncated basis. So I could take my psi of r and I could write it as, let's say, a coefficient a times some wave function psi a, coefficient b, wave function psi b, and so on. And if I pick these specific functions as my basis with unknown coefficients a, b, and c, then minimizing over that particular subspace of functions does correspond to ordinary calculus. That corresponds to trying to minimize the function e depending on those three coefficients in the usual way. Because then my e of psi of r becomes a function e of a, b, and c. If these are specific functions, like, I don't know, this is a constant, this is a line, this is a parabola, I can plug those in, calculate the integrals separately, and I get an expression. A function, not a functional, a function that depends on specific values. And then once I have this, I can minimize it using regular calculus. with respect to A, B, and C, whatever parameters I've got. So you'll do the usual song and dance, take the derivative, set the derivative equal to 0, verify that it corresponds to a minimum. So you will require derivative with respect to each of the parameters is equal to 0. And then verify that it is a minimum using one method or another. Negative compounding. You don't want a saddle point, you don't want a maximum, you want an actual minimum of the function. So one particular place that this is useful is in quantum chemistry. I'll give you an example from that in a moment. So clearly, the only other physics that remains to be done here is to choose which functions you use to try to minimize the energy. You could make as simple or bad a choice as you want here and then still apply it. The usual thing you do when you have no idea what to do is just pick a Gaussian. Gaussians are easy to integrate, plug it in, put some parameters on it, and run with it. So one simple trial function that we will use a lot is a Gaussian. So you could take, for instance, in one dimension, psi of x equals, you have some overall normalization. The normalization doesn't even really matter. And you can have e to the minus, let's say, 1/2 alpha x squared. Normalization will drop out of the integral overall, right? You'll integrate it upstairs, you'll integrate it downstairs. So without loss of generality, we can just set the normalization equal to 1. And then this becomes a wave function that depends only on your choice of parameter. So this would lead to an energy functional that reduces down to a function of the parameter alpha. And then you will just minimize with respect to alpha. You'll do this, you'll compute the minimum energy, and that is your estimate for the ground state. So when you have no idea what else to do, try a Gaussian, but there's not a whole lot of physics that goes into that. The better your physics input, before you try to minimize, the better the final estimate will be. And one place that that's particularly useful is in quantum chemistry. Where a natural choice, if you want to calculate the electronic wave functions of molecules, which are incredibly complicated things, good luck solving them exactly, is to take as your basis a linear combination of atomic orbitals. Linear combination of atomic orbitals. So one example with this is to consider, for instance, the molecular hydrogen ion, 2H+. That is, you've got one proton, you've got another proton, and you've got exactly one electron floating around between them. What do I do for the wave function of this thing? Psi of r equals what? Difficult problem to solve in general. I think this is one of the last remaining problems that can be solved exactly in quantum mechanics. It requires funky things like elliptical coordinates and separation of variables in elliptical coordinates. But rather than doing that, you can make a physically motivated choice for how you want to try to minimize the energy. And that is to say that my wave function psi r of the ground state should be some superposition of, let's say, the ground state wave function of this hydrogen atom and the ground state wave function of that hydrogen atom. So you can take a superposition of the 1s state of, let's say, r plus r over 2, plus or minus psi 1s of r minus r over 2. So here, I'm using capital R to denote the separation vector from one proton to the other one. So this just says I've got a ground state wave function centered on this guy at minus r over 2, and I've got another one centered on this guy at plus r over 2. The ground state wave function is really simple, right? The ground state wave function of hydrogen, especially if I don't care about normalizing the thing, is just a decaying exponential. So this is e to the minus absolute value r plus r over 2 divided by the Bohr radius plus or minus e to the minus r minus r over 2 absolute value divided by the Bohr radius. Simple decaying exponentials. The plus or minus, I don't know a priori which one I want to pick, but I can use physical insight to tell me which one's going to have lower energy. If I've got one proton here, one proton there, this wave function looks like a decaying exponential centered here. This wave function looks like a different decaying exponential centered here. I can either add them up together or I can subtract them. This is very much like our discussion last week about identical particles, bonding versus anti-bonding states. So if I add them together with a plus sign, then my overall wave function looks like this. I'll have a peak, a valley, but I will accumulate some density in the middle. There will be a significant probability for the electron to hang out in between. If this is triggering chemistry memories, then this is because this is related to a covalent bond. If I have negative charge density that likes to hang out in between the two protons, that's going to lower the energy. It's going to lower the kinetic energy because the wave function is pretty smooth there. The derivative is not very big in between. It's also going to lower the potential energy because I've got negative charge density close to both of the positive charges. The other alternative, if I can squeeze it in down here, would be the one which goes up and then down through zero and back. This one does the opposite. This increases the kinetic energy because I've got a steep slope. It has to have a node in the middle. It passes through zero. So that will increase the kinetic energy. It will also increase the potential energy because you will not have density sitting in the middle. The electrons will be repelled away from the center and they will want to hang out over here on the edges. So that will have higher kinetic energy because of the node in the wave function. It will also have higher potential energy. So this is referred to as an anti-bonding state. So based on this physical insight, I say I want to take a superposition of the hydrogen ground state. I know for sure that before I even get started, that the one that's going to have the lower energy is the bonding state with a plus. It's going to be this one. So all I have to do is take this thing and then minimize it with respect to, let's say, the proton separation R. When I do that, that will give me an estimate for the bond length, the typical distance between the two protons, and the binding energy. So I will not make you suffer through the calculation of how to do that. We will start off with some simpler examples in a minute. But I just want to show you what this looks like physically. Okay, let me jump to the notes. Yeah, so here's the two states. You've got a bonding state, which is the symmetric combination that increases the density in the middle, leading to a covalent bond. You have the anti-bonding state, which produces a node in the middle, which increases the kinetic energy, and the electrons hang out on the opposite sides. If you take the symmetric state and you look at the energy functional, so you take that wave function, you plug it in, you do all of the painful integrals, you get an energy which is a function of the nucleon separation R compared to the Bohr radius. And if I plot that function, then this is what I get. This is the binding energy. So in units of Rydberg, which is the ground state energy of one hydrogen atom, you see that the two of them together have a minimum energy at a characteristic distance. This -1 Rydberg would correspond to an unbound state where you basically got one electron hanging out on one proton, whose energy is -1 Rydberg, and the other proton is infinitely far away. So when you calculate the binding energy, it's the binding energy compared to -1 Rydberg. And you see that, yes, actually the two states together with the electron density hanging out in the middle is more stable and has positive binding energy. If you find that variational minimum, you find that the minimum happens at about 2.5 Bohr radii, and you find that the binding energy compared to -1 is about 1.77 electron volts. That's what you get from minimizing the simple wave function. It is okay, but it is not a spectacular approximation to the truth. The true solution is much closer to 2 Bohr radii for the bond length, and the binding energy is stronger, so that depth is lower, as required by the variational principle. The binding energy is 2.8 eV. So from this simple starting point, just using the hydrogenic ground state, you could improve your variational estimate. You could include p-wave states. You could just expand the basis in this way. You can also include more flexible parameters. One thing that you can do is you can say, let me imagine that my electron wave function screens the charge of the proton. And so then you can replace the charge squared of each proton with an effective charge, with the new parameter Z, and you can also minimize with respect to Z. So good physics choices can lead to meaningful output, but if you put in garbage, you get out garbage. And then as we will look at again in a moment when we actually do a variational calculation of the ground state energy of hydrogen, one problem with this is that you do not know how good your estimate is. So you go through all this math, you calculate the final answer, and you say, okay, 2.54 radii, 1.77 electron volts. Is that a good answer or a bad answer? You have no idea, because this is an uncontrolled approximation. You do not know a priori how small the corrections are to this estimate without further calculation. Okay, this is what I wanted to show you about physics applications. Now I want to move on to actually doing this in practice for some simple examples, first out of the textbook, and then we'll see how much time we have, and I want to at least flash you and walk you through the complicated problem that was actually given in 2017. Any questions before we go through some examples? Okay. So simple examples. Consider a quartic potential in one dimension. V of x is lambda x to the fourth. And for our trial wave function, when you don't know what else to do, try Gaussian. Psi of x is e to the minus 1/2 alpha x squared. And we will minimize with respect to alpha. So we want to set up the variational calculation. The energy associated with any trial wave function is in one dimension integral dx, psi star of x. The Hamiltonian is p squared over 2m plus v of x, psi of x, divided by the normalization, integral dx, psi of x, absolute value squared. Where, of course, since we're working in coordinate space, we should use the coordinate space representation of the momentum operator. This will be minus h bar squared over 2m, d squared dx squared. So if I plug in the specific function that we've got here, the thing that I want to minimize is not some scary, complicated functional. It is just a function of alpha. So what I get is e of alpha is equal to integral dx, e to the minus 1/2 alpha x squared, minus h bar squared over 2m, d squared dx squared, plus lambda x to the fourth, psi of x, where psi of x is e to the minus 1/2 alpha x squared, divided by integral dx, e to the minus alpha x squared, where I've multiplied both exponentials together. For the sake of me keeping track of all of the algebra we're going to have to do, I'm going to call this the numerator and I'm going to call that the denominator. Let's start by evaluating the denominator. This one's a simple Gaussian integral, minus infinity to plus infinity dx, e to the minus alpha x squared. If you commit one integral to memory, this is the one that it should be. What is the answer?
Is that square root of pi?
Square root of pi divided by alpha. So, okay, great, good job. Now for the hard part. Let's do the numerator. Integral minus infinity to plus infinity dx, e to the minus 1/2 alpha x squared minus h bar squared over 2m d squared dx squared plus lambda x to the fourth e to the minus 1/2 alpha x squared. First thing I got to deal with is that kinetic energy. I need to take a couple of derivatives. So let's start by tackling this piece. Part number one is equal to minus h bar squared over 2m d squared dx squared e to the minus 1/2 alpha x squared. When I take the x derivative, the exponential remains the same, and I bring down the derivative of the numerator by chain rule. So this is minus h bar squared over 2m one extra derivative after I've done the first one, that brings down minus alpha x e to the minus 1/2 alpha x squared. Now I've got to take another derivative. Now I have to deal with product rule. I can differentiate the first term or the second term. So continuing, part 1 is equal to minus h bar squared over 2m. If I differentiate the prefactor, I get minus alpha e to the minus 1/2 alpha x squared. If I differentiate the second factor, I bring down another factor of minus alpha x plus alpha squared x squared e to the minus 1/2 alpha x squared. So I get minus h bar squared over 2m minus alpha plus alpha squared x squared e to the minus 1/2 alpha x squared. And make sure my algebra hasn't gone off the rails already. Yes, good. Sorry? So on this one, I took a ddx on it and I killed the x there. So I just get minus alpha. So this first term came from hitting ddx on minus alpha x. So I just got minus alpha. Okay, so I plug it back in and now I have to do this integral over x. So this gives me numerator equals integral minus infinity to infinity dx. Now, since I'm done with derivatives, I can safely pull across this factor and combine it with this one. And I'm left with the algebraic expression minus h bar squared over 2m minus alpha plus alpha squared x squared plus lambda x to the 4th e to the minus alpha x squared. This is a Gaussian integral, so we should be able to do it. Some of the terms are just constants, but some of the terms have x dependence in them. So you've got to deal with the integral of x squared times the Gaussian and x to the 4th times the Gaussian. Here's where a simple trick can help you. You can think of taking a derivative with respect to the parameter alpha. Notice that if I take dv alpha of e to the minus alpha x squared, that I bring down minus x squared, and I still keep the exponential hanging around. So what I can do is I can associate minus x squared with dd alpha. Because if I take that derivative, I can generate the factors of x squared that I want. So inside the integrand, I can replace, without loss of generality, every instance of x squared with minus dd alpha, acting on that exponential at the end. So when I do that, dd alpha will bring down x squared. 2 of them will bring down x to the 4th. That will then make this object independent of x, and then I can yank it out of the integral.
If you bring down 2 dd alphas, are we bringing down a dd alpha squared or d squared d alpha squared?
The second one is 2 derivatives, d squared d alpha squared.
Okay.
So when I do this, I get numerator is equal to, I'm going to take that expression in brackets, replace x squared with minus dd alpha, and pull the whole thing out. So I'm going to get minus h bar squared over 2m. I have negative alpha plus alpha squared. I have x squared becomes negative dd alpha plus lambda, and then I'm going to bring down 2 negative dd alphas, which is d squared d alpha squared. After having done that, I pulled out all the non-trivial stuff from the integrand, and I'm back to my favorite integral in the world, e to the minus alpha x squared, which everybody knows by heart is square root pi over alpha. Now I can take derivatives of something simple to get my answer. So square root of pi is hanging out in front. That has nothing to do with anything. Minus h bar squared over 2m minus alpha squared dd alpha plus lambda d squared d alpha squared. And the thing I have to take derivatives of is alpha to the minus 1/2. Of course, dd alpha of alpha to the minus 1/2 is minus 1/2 alpha to the minus 3/2. And if I have to take 2 derivatives, I just do it again. And I get plus 3/4 alpha to the minus 5/2. So now I replace those derivatives by the answer. I get numerator equals square root of pi minus h bar squared over 2m. Now in the first term, I didn't have any derivatives, so I still just have alpha to the minus 1/2. I had alpha to the 1, alpha to the minus 1/2. That gives me negative alpha to the positive 1/2. Minus, from the first derivative, I have alpha to the negative 3/2 and 2 more of them upstairs. That again gives me alpha to the 1/2 with a factor of minus 1/2. Plus lambda, and then I had the second derivative piece. The second derivative piece gave me 3/4 alpha to the negative 5/2. So I get 3/4 lambda alpha to the minus 5/2. And then you can simplify this combination a little bit. Square root of pi, I've got negative 1 and positive 1/2, so I get negative h bar squared over 4m alpha to the 1/2 plus 3/4 lambda alpha to the negative 5/2. And that's my expression for the numerator. Oh, except I can't do minus signs. I had a minus out front. Negative 1 and positive 1/2 is a negative 1/2, so that cancels the minus. That's better. Okay, so now I plug it all back into my functional. E of alpha was my numerator divided by the denominator. It's this thing where my denominator was root pi over alpha, obviously. So I cancel the root pi, I put another factor of square root alpha upstairs, and I get h bar squared over 4m alpha plus 3/4 lambda over alpha squared. Now there is a little bit of physics that you can identify from this, or I guess it's a little bit of mathematics. So these two terms prefer different values of alpha when you're trying to minimize. The kinetic energy piece is minimum when alpha goes to 0. The kinetic energy is least when the wave function goes to a constant, when the wave function is very broad. But if the wave function is very broad, then it gets severely penalized by the potential energy, which is quartic in x. So the potential energy prefers something which has alpha going to 0. You want something which is very minimum here. Other way around. Alpha goes to 0 is the broad one. This one wants alpha going to infinity, like it's a delta function sitting at the origin. So there's a competition embedded here between the kinetic energy and the potential energy. The kinetic energy prefers alpha goes to 0, which is very broad. That minimizes the slope or the derivative of the wave function. Something which goes to a constant is very good for the kinetic energy. The potential, on the other hand, prefers alpha going to infinity, something which is a very sharp delta function. So there's going to be a minimum somewhere in between. That's what we've got to find. That is another unfortunate thing about the variational principle. You go through all of this laborious work to calculate the functional, and you're not done yet. You just set up the problem. Now you've got to minimize the damn thing. In this case, it's not so bad. So we need to minimize E of alpha. So we need to require dE d alpha is equal to 0. So if I take the derivative with respect to alpha, I get a constant from the first term. That's nice. The second term is alpha to the minus 2. So I get minus 3/2 lambda over alpha cubed. And I want this to be equal to 0. So I solve algebraically for alpha. 3/2 lambda over alpha cubed is h bar squared over 4m. So I get alpha cubed is equal to, I multiply this across, 6 lambda m over h bar squared. So alpha is the cube root, 6 lambda m over h bar squared. So this is at minimum. You might call that alpha minimum. In this case, there's only one solution, so I'm pretty darn sure that this is the minimum. If there were multiple solutions, then you've got to start worrying about which one is a minimum, which one is a maximum, could it be an inflection point or something else. But in this case, there's no such worry. Guess what? You're still not done. This is only the position at which the minimum occurs. You need to find the energy of the minimum. So you need to take this value of alpha and plug it back into your energy function. So I look at the energy at the minimum, E of alpha min is equal to h bar squared over 4m times 6m lambda over h bar squared, 2 to 1/3 plus 3/4 lambda, 6m lambda over h bar squared to the minus 2/3. And you simplify, you do a little algebra, and at the end of the day, you get 3/8 6 h bar to the 4th lambda over m squared to the 1/3. Hooray! What did I learn from all of this exercise? There is a minimum. It comes from a competition between kinetic and potential energy. I get a number. How accurate is that number? I have no idea. Could be a good answer, could be a bad answer. Depends on how good the assumption that I have a Gaussian is to the correct truth. So this emphasizes that this is an uncontrolled approximation. A priori, you do not know how large the corrections are. How large the corrections or the error is. So there are certainly limitations to perturbation theory, but the virtue of perturbation theory is that you always know how big the corrections are. You have a coupling constant, and if you calculate the first order in G, if G is 10%, then you're pretty sure that the typical size of your next to leading order corrections is 1%. It's G squared. Here, the corrections could be 10%, 50%, 100%. No idea. Questions?
This is the minimum energy.
Yes.
Not the minimum. The minimum below it.
This is, yeah, so this is the minimum energy of the function that we chose. The true, yeah, so that's a good point to emphasize. So the true ground state energy is always less than or equal to E of alpha min. So all we have really derived is an upper bound, E naught less than or equal to 3/8 h bar to the 4th lambda over m squared to the 1/3. Yeah, so this is the strict statement that for this particular choice, we found this, which is an upper bound for the truth.
So this is the upper limit for the ground rated energy.
That's correct.
Is there any other technique to find the lower limit? This minimum energy, E naught, maybe it will go to minus infinity.
Yeah, so only in very special cases do you know that you have a lower bound as well. So if you have a Hamiltonian that is positive definite, for instance, then you'll know that the energy needs to at least be above 0. And then if you have a floor at 0 and you have some limit above, at least you can squeeze it from both sides. But if you could have a bound state with negative energy, hard to say.
There's no any other way.
This method does not give you any constraints coming from a lower bound. If you have separate information that tells you about a lower bound, then you can use that to help you out. But the variational principle by itself does not. It's only a way to get an upper bound. Any questions on this simple example? Okay, we do not have a ton of time. I want to at least run through the core of the next exercise. I want to show you what was actually asked on the 2017 comprehensive exam. Okay, so another thing that you can do in a similar way is you can estimate something we do know the correct answer to. Estimate the ground state energy of hydrogen. That means we're going to take the Coulomb potential. V of R in 3 dimensions now is minus E squared over R. And let's take again our favorite trial wave function, which is a Gaussian. So let's try psi of R is E to the minus alpha R squared. Now there is a little bit of physics to this choice, because now that we're talking in 3 dimensions, you could have whatever angular structure you want. This assumption assumes that the ground state is S-wave, that it is spherically symmetric. That is a good assumption. Spherically symmetric. And so this is this uses our intuition that the energy should increase with angular momentum, kinetic energy. So trying L equals 0 is a good physics input that will help you estimate the minimum energy. Okay, so what do? Now you have to set up your functional E of psi in 3 dimensions. E3R, psi star of R. Your Hamiltonian is minus h bar squared over 2m, Laplacian minus E squared over R. Psi of R divided by integral d3r, psi of R squared. So one thing to keep in mind is the radial versus angular decomposition of the Laplacian, because that's where the angular momentum part comes in. In 3 dimensions, the Laplacian is equal to 1 over r squared ddr, r squared ddr, plus or minus, I always forget. If I put in the minus h bar squared over 2m, then I get plus L squared over 2m r squared. So that this looks like radial kinetic energy and rotational kinetic energy. Because we're dealing with a spherically symmetric wave function with L equals 0, we know that this wave function is an eigenfunction. L squared acting on psi of R, which is spherically symmetric, is h bar squared L plus 1. Psi of R, this is an eigenfunction with L equals 0. So even though this is a 3-dimensional problem, the angular part isn't doing anything. The L squared part is going to go to 0 for this wave function. That will not be true for the question that was asked on the comprehensive exam. Everybody with me on this part? Right, 3 dimensions, 3-dimensional kinetic energy, radial part. Angular part does not contribute because we've got a spherically symmetric wave function. Okay, so let's do the denominator. Fix the normalization. We have denominator equals integral. R goes from 0 to infinity, dr times r squared. I have integral d cosine theta from minus 1 to 1. I have integral d phi from 0 to 2 pi. Times the product of the wave function is e to the minus 2 alpha r squared. So far, so good. The angular part does nothing. So in fact, we could have canceled this out from the beginning. The angular integration just gives me the total solid angle 4 pi. I get a factor of 2 from the cosine, I get a factor of 2 pi from the phi. So life is fairly good for right now. I have 4 pi integral 0 to infinity dr times r squared e to the minus 2 alpha r squared. I say, woohoo, it's a Gaussian integral, and I immediately write down the answer, except what's the problem?
Yeah, it's a gamma function.
It's not a gamma function, thankfully. That would be even worse.
The integration limit is not from minus infinity to infinity.
So, yeah, so one problem is the r squared. The other problem is the limits. The limits do not go from minus to plus infinity. That special square root of pi thing is only true for minus to plus infinity. Yeah, so the r squared is a problem. I can get around the r squared using the same trick by dd alpha. And I also have to deal with the limits. How do I deal with the limits?
You just take half of the integral.
Yes, exactly. Because this is an even function, I can just take half of the symmetrized limit from minus to plus infinity. That would not be true if I had an odd power of r, but because I only have even powers, I can. Very good. I think I told you no too quickly, Nicholas. Maybe this is reducible to a gamma function. I don't remember the specific factors that go into it off the top of my head. So my denominator is equal to, I have 4 pi. The r squared I can get from, let's see, minus 1/2 dv alpha. And I can, for the price of another half, complete the integral to go from minus to plus infinity. dr e to the minus 2 alpha r squared. This is now my favorite, square root alpha divided by, pi divided by 2 alpha, because of the 2 in the exponents. So now I clean things up. I've got 1/4 minus sign. I get minus pi root pi over 2 dv alpha of alpha to the minus 1, and I get plus pi square root pi over 2 alpha to alpha to the minus 1/2, excuse me. So I take the derivative and I get plus pi over 2 square root pi over 2 alpha to the minus 3/2. Why does this not look familiar? Because in the notes I cancel the 4 pi. So if I divide out the 4 pi, I get the 1. Yes, I'm happy with this. Okay, that was the easy part. Setting up the numerator is the hard part. We only have about 10 minutes, so I think I'm going to have to set up the integrals and then jump to the answer. All of the algebra is in the notes for you guys to follow through. So in the numerator, I have integrals 0 to infinity, dr r squared. The angular integral is blessedly going to give me just a factor of 4 pi. I have minus h bar squared over 2m, 1 over r squared, ddr, r squared, ddr, minus e squared over r. I have the wave function in front, which is e to the minus alpha r squared. I have the wave function at the end, which is e to the minus alpha r squared. So I've got to calculate a whole bunch of derivatives. I have to take these derivatives on that function. After laborious calculation, you get minus 6 alpha plus 4 alpha squared r squared, e to the minus alpha r squared. So then I get 4 pi integral 0 to infinity dr minus h bar squared over 2m. I'm going to distribute this factor of r squared into the integrand. And I get minus 6 alpha r squared plus 4 alpha squared r to the 4th minus e squared times r times e to the minus 2 alpha r squared. R squared, r to the 4th, and r. So you got a whole bunch of integrals to do. Now you need to do the radial integrals. Integral 0 to infinity, dr r squared, e to the minus 2 alpha r squared. You need to do integral dr r to the 4th, e to the minus 2 alpha r squared, 0 to infinity. You also have to do one with an odd power. You also have to do 0 to infinity, dr times r, e to the minus 2 alpha r squared. These two we can do by our standard trick like before. These are even functions of r, so I can symmetrize the integrand with a factor of 1/2. I can get r squared by dd alpha. Same techniques work. So for these ones, I wrote them separately. Okay, I'll just write the final answer on this one. This one, however, you cannot do the same way. This has an odd function of r, so you cannot symmetrize it to make the Gaussian integral. What should you do instead?
integration by parts?
Integration by parts might work. But you can do something even simpler. Direct substitution is enough to do. If I just take u is minus 2 alpha r squared, then du is minus 2 alpha r squared, yes. I get 4 alpha r dr, and that r dr is exactly what I have. So this is equal integral 0 to infinity du over 4 alpha e to the minus u, and then you can do it by element 3 methods. Integration by parts might work. You have to be careful about how you handle the Gaussian. So what I get for this one is just 1 over 4 alpha. So after lots of laborious calculation, you have finally done all of the integrals, you've evaluated the numerator, you divided by the denominator, and you get your functional of alpha. E of alpha is numerator divided by denominator equals 3/2 h bar squared over m alpha minus 2 root 2 over pi e squared alpha to the 1/2. Congratulations, you are still not done. You still have to minimize it. So you have to set d alpha equal to 0. 3/2 h bar squared over m, let's see, minus root 2 over pi e squared alpha to the minus 3/2. No, alpha to the minus 1/2. You solve the equation and you get alpha equals 8 divided by 9 pi e to the 4th m squared over h bar to the 4th. In this case, we know what the exact answer is. So when I plug it back into the energy, I get E of alpha min, and I plug it back in, and I get minus 4 over 3 pi e to the 4th m over h bar squared. This is minus 1/2 mc squared. Alpha E and m is e squared over h bar c squared times that numerical factor, 8 over 3 pi. I had 4 over 3 pi and I needed the 1/2. This is the exact ground state energy. And this factor is 0.85. So this variational estimate gets you within 15% of the correct answer. So sometimes it works, but for the wrong reasons, right? So you got a pretty decent estimate. The Gaussian was not too far off from the true solution, which is not Gaussian, but which is decaying exponential. Again, very hard to know from the start whether it's a good idea or a bad idea. Any questions on this example?
If we saw this question, why wouldn't we just guess that it's decaying exponential, knowing the answer?
Probably because the question would tell you you must use a Gaussian to avoid you from immediately getting the correct answer. If they said estimate the ground state energy using variational methods, sure, you can guess the decaying exponential and immediately get the exact answer. For that matter, you can probably just say, what if it's a decaying exponential? Aha, observe that it is an eigenstate of the Hamiltonian. Therefore, this is the answer. So I think that's it. Any questions on these simple examples from the textbook? Okay, in my remaining 5 minutes, I want to show you something that I have some real beef about. No, not my midterm, I'm fine with that. Okay. Blah, blah, lots of algebra. So this was the 2017 comprehensive exam. This in particular is problem number 4. Devise a variational calculation of the polarizability of the hydrogen atom. Simple procedure would be to take a linear combination of the 1s and the 2pz states. So they give you this sort of simple way of thinking about it. You say the ground state is the 1s state. Imagine that it has a little bit of a mixture from the 2p state. That mixture will allow it to have non-zero dipole. and therefore you can get a polarizability out. So the suggestion in terms of your trial function is something which is pretty simple. You take the 1f state, which is that decaying exponential, and you multiply it by 1 plus a times z, where a is your variation point. That's not too bad. Z is r cosine theta. So now your angular stuff will not be completely trivial, and you can imagine minimizing with respect to a. The wrinkles keep coming, right? So this is minimizing with respect to the Stark Hamiltonian, which is the kinetic energy, the Coulomb potential energy, and the external electric field, EZE. So there are several terms that will enter into the Hamiltonian. The exercise is to do the minimization, find the best energy, and identify the polarizability. So this is a problem that you do not want to start running through the math without a clear idea of where you're going. So few words about what you're going to see when you do this exercise. So you say, okay, I have 1 plus a times z times psi 1s. Psi 1s is up to some normalization, e to the minus r divided by Bohr radius. There's lots of a's floating around. So personally, I felt like I did not want both a and ab because I'm probably going to get confused. So I chose to write k as the inverse of the Bohr radius so that I'm not going to mix them up until the end. So this is not too bad. 1 plus ar cosine theta e to the minus kr is my wave function. The Hamiltonian is messy. The Hamiltonian is kinetic energy, Coulomb potential energy, and external electric field. The kinetic energy now has a non-trivial angular point. The L squared is not 0 because now you contain a mixture from the p wave states. The p waves have L equals 1. So you're going to have many terms that you have to calculate. So you'll set up the variational estimate like we did before, and you'll minimize with respect to A. How are you going to find the polarizability at the end of the day? The polarizability was something that we talked about for the second order Stark shift, for a state that does not have a dipole moment to begin with. This is a coefficient that multiplies the electric field squared dependence. So when you do this, you'll find whatever the minimum value of A is. And it may not be obvious, but your function is going to be some complicated function of the electric field. It's not going to look like a simple constant plus electric field squared. So you need to know that in order to identify the polarizability, you're looking at the weak field limit, the limit when the electric field is going to 0, and you're looking for that quadratic dependence. So you will be doing a Taylor series of this object for small electric fields to help you pick out the quadratic piece. There will be a constant independent of the electric field that has nothing to do with finding the polarization. The polarizability is that coefficient, 1/2 alpha electric field squared. So the exercise is do all of the laborious math to find the minimum. After you've found the minimum, expand for small values of the electric field and find the coefficient of the electric field squared. This is equivalent, by the way, to saying take 2 derivatives with respect to the electric field and then set it equal to 0. So, okay, I just want to flash you through what goes into the next 6 pages of this calculation. I think you get an idea as to why this is going to be challenging. But frankly, it took me 2 hours with the benefit of Mathematica to check my math and make sure I wasn't going off down the wrong avenue. You guys had 1 hour to do this under time constraints with 3 other problems to solve. Right, 4 hours for 4 problems. Correct me if I'm wrong. That's the comprehensive exam, right? I'm pretty sure that's the case. 4 hours for 4 problems. If you have 1 hour to do this with nothing else, and you have to wrestle with conceptual slipperiness, laborious algebra, and the time constraints, this strikes me as profoundly unfair. This makes me angry because I feel like the person who assigned this did not take into consideration at all the conditions under which you have to solve this problem. If this was part of a take-home exam, all's fair in love and war. If you had Mathematica or some other computational resource so that you could focus on setting up the algebra and then hitting enter to let it do all of the algebra for you, then again, that would be fair game. But all of these 3 things together, that struck me as extremely unacceptable. So what would you have had to do if you knew automatically exactly what you had to do? You have to set up the integration. The denominator is now non-trivial because the angular integration involves this cosine squared business. So when you expand the parentheses, you have integral over cosine, a constant, something linear, and something quadratic. Angular integration is your friend. The constant goes to 2. The linear term, angular averages to 0. The quadratic term gives you 2/3. So angular integration is a good thing to do first before you attempt to do the radial integrals. You will kill some terms and simplify others. So you do this, and then you get radial integrals much the way that we had before, r squared and r to the fourth. You can pull them out by derivatives, and you can symmetrize the integration. Actually, sorry, it's not Gaussian. You don't need to symmetrize the integration. It's just the decaying exponential. So you do that explicitly. You end up with derivatives on K inverse. You have up to 4 of them, so you tabulate it. And at the end of the day, you get something simple for your denominator. That is the easiest part. Setting up the numerator is quite laborious. You have the radial part now, which brings in lots of mixed things with the sines and cosines. The orbital part, the angular momentum, is now non-trivial. You need to recognize that when L squared is acting on the S wave piece, that's going to give you 0. But that admixture from the P wave state, that is an eigenfunction with L equal to 1. So when that angular part acts on the P wave mixed contribution, you'll get 2 h bar squared out. So again, you get a non-trivial contribution from the angular parts. Plug it back in. Now you've got all of this stuff with angular integration and radial integration. Angular integration is your friend. Angular integration will help you simplify. Anything that's linear or cubic in cosine will go to 0 by symmetry. You only have to keep the even functions. So cosine to the 0 gives you a factor of 2. Cosine of theta gives you 0. Cosine squared gives you 2/3. Cosine cubed gives you 0. After you do that, now again, you are left with a ton of radial integrals. Those radial integrals are doable. You get, again, derivatives that you can pull down. There's minus signs. You tabulate them all. At the end of the day, you get something which is tractable for the numerator. Lots of opportunities to go off track. Then you divide by the denominator to get the energy functional. Finally, something that you can do something with. This is still not finished. You have to minimize it. Take the derivative with respect to that A parameter or equivalently in units of the Bohr radius and set it equal to 0. If I take the derivative of the functions, I set it equal to 0. Lovely, I get a quadratic formula. There are 2 solutions now, not just one. The 2 solutions that you find involve square roots of the electric field. This is the complicated function of the electric field I was talking about. Not obvious how to extract polarizability out of this. You need to know that once you get to this point, you're really interested in the small electric field limit, where I approximate the square root by the binomial theorem. Then I get my 2 formulas, something that goes like 1 over the electric field and something that goes linear in the electric field. This is the one that makes sense. The amount of induced dipole moment, right, the amount of mixture that you get between the S and the P wave state is proportional to the electric field. So this looks like you started off in the S wave state, you turned on the electric field, and you mixed in a small percentage of the P wave state. That's your induced dipole moment due to the electric field that's going to lead to a polarizability. So you need to recognize that this is the solution that you want, plug it back into your energy functional, expand it all for small electric fields, and then finally, at the end of the day, you get something aggravatingly simple. And you get the polarizability is 4 times the Bohr radius cubed. So the result that you get out of all of this, that 2 Bohr radius cubed electric field squared, you just need to recognize that that term is 1/2 times the polarizability times the electric field squared. So you can compare this to actual answers. If you compare this to first order in perturbation theory, you get about 3. The exact solution is more like 4.5. So as a variational problem, this is not too bad. But like I said, considering that it took me 2 hours to work through all of this and about 8 pages added onto the notes, I think I'm going to have some words for my colleagues when it comes time to design the comprehensive exam for this year. Because clearly this problem was not tested under test conditions. But I feel like you needed to see this to know what has been expected of people in the past, so that you will see what could come. All right, that is the end of my tirade against the variational principle. Any questions, concerns, other complaints that you would like to voice?
Profoundly discouraging.
I'm sorry to say that. I want to show you the truth and then fight to change it. All right, thank you guys very much. Hopefully we'll have something a little more uplifting on Wednesday when we will quantize the electromagnetic field. Hopefully we'll end the semester on a high.
I have a question, Doctor.
Yes, sir.
Would you be available tomorrow for a Zoom meeting anytime or on your regular office hours?
Both. If you'd like to speak tomorrow, we can schedule a time for that. That's fine.
Okay. Yeah, I'll email you then.
Okay, send me an email and we'll set up a time.
Okay, yeah.
Sounds good.
Thank you, Doctor.
No problem.